Welcome back to Differential Calculus. In this video, I want to talk about a really powerful technique, which is called logarithmic differentiation. With this is pretty much going to wrap up all the derivative formulas and techniques we have, because after you know how to do this, you will be able to differentiate everything. So let's get right down to it. First of all, it relies on this fact. If we have y equals log x, we take the derivative, y prime is 1 over x. Okay. Logarithmic differentiation, believe it or not, uses the logarithm every time, so we need to know how to differentiate log x. So first, let's just practice differentiating log of some functions of x. Say we want to differentiate natural log of 3x squared plus 1. So this is just a chain rule, right? Here's my outside function is log, inside function is 3x squared plus 1. So what do? We take the derivative of the outside function, that's 1 over. Derivative of log is 1 over, so I just do 1 over the stuff that was inside, times the derivative of the stuff that was inside. Derivative of 3x squared plus 1 is just 6x. I usually simplify this to be 6x divided by 3x squared plus 1. So notice what I have. I have the derivative of the inside divided by the stuff that's inside. And that's always how it's going to work. Let's try another one. Say I want to differentiate natural log of cosine x. This is actually important in calculus too, differentiating log of cosine x, believe it or not. So what am I going to do? Well, again, I have the chain rule. Here's the outside, here's the inside. So I do derivative of the outside. Derivative of natural log is 1 over. I have 1 over the stuff inside, that was cosine x, times the derivative of cosine, that's the inside, times minus sine x. Okay, now usually I would write this as minus sine x over cosine x. And of course you can write this as negative tangent x. The reason this is important in calculus too is because if you want to know what function has derivative tangent x, it's negative natural log of cosine of x, believe it or not. And again, let's just note that this is the derivative of the inside divided by the inside function. And that's how logarithmic derivatives always work. When you take the log of a function, you get the derivative over the function. Because, well, it kind of just pops out of the chain rule. So if I want to say, let's say I have natural log of f of x, and I take the derivative, I always get f prime of x divided by f of x. Or if I have ln y, and I take the derivative, that's always going to be y prime over y. Right? It always works that way because of the chain rule. Okay, so we're going to use that a lot. Let's talk about logarithmic differentiation. So this is a technique. It's like an algorithm, a series of steps that you go through, and most of the steps are easy. One of them is sometimes hard, the derivatives part. But the other steps are all just, you always do it the same way. So we have some function, f of x, we want to take the derivative. It does not involve a logarithm. We introduce the logarithm, believe it or not, to make it easier. I know you're thinking, why would that make it easier? But it does. So here are the steps. Let me talk about them in general, and then we'll do a few examples. So step 1 is we make this an equation. Okay, so you always have to have an equation because we want to do the same thing to both sides. Okay, so we always make an equation, by which I mean y equals f of x. So you just let y equal whatever you're differentiating. So if I'm differentiating cosine x, I would let y equal cosine x, like that. Okay. Now what I want to do is I want to take the natural log of both sides. So I end up with natural log y equals natural log f of x. Okay, making it worse. The thing is, the times you use this are times when natural log f of x can simplify. Okay, so next what you want to do is you want to simplify natural log of f of x. So maybe f of x has some messy exponents. Maybe it's got a bunch of square roots and fractions and stuff that you can use properties of logarithms to simplify. Okay, so that's not always the same. It's different each time, but usually not too bad. Now that we simplified, we take the derivative of both sides. So I mean both sides of this equation. On the left, I'm going to get y prime over y right? Because I take the derivative of log y, I get y prime over y by the chain rule. That's from implicit differentiation there. On the right, I get f prime of x divided by f of x. If, or other stuff. Let me actually not say that. Usually you simplified log of f of x so much that you get other stuff. It's just whatever you happen to get. You do the derivative of log f of x. That's the part that's different every time, and it can be very complicated. And then finally, you solve for y prime. Because remember, y prime is what we want, right? We want the derivative of f of x. Y is f of x, so we really want y prime. So we solve for y prime. That just means take this y here and move it over to the other side. So y prime equals y times stuff that was on the right. And then finally, you replace y by f of x. Because you want your answer to be y prime equals only stuff involving x, not y's and x's. Oops, just y by f of x. Okay, so that seems like a big, long thing. It's not actually that bad. I just wanted to make sure you had all the steps so you know what to do every time. But in practice, it's not that bad. So let's try it on this function. And boy, I dare you to try to differentiate x to the x without logarithmic differentiation. I mean, good luck, right? But with logarithmic differentiation, we can do it. So what am I going to do? I'm going to write an equation. Let's let y equal x to the x. I do that so that I can do the same operations on both sides of the equation. Okay? So now I'm going to take the natural log of both sides. Ln y equals the natural log of x to the x. And the beautiful thing about natural log is, regardless of what I know how to do with x to the x, I do know that when I do natural log, I can pull the x out in front. So I really have, this tells me the natural log of y is equal to x times the natural log of x. Logarithms are so powerful because they turn that horrible x to the x exponentiation into just multiplications. I know how to differentiate x log x, right? So now I'm going to differentiate both sides. So I take the derivative with respect to x of log y. That must be the derivative of the other side. Both of those are easy, right? Derivative of ln y, it's implicit differentiation, but I can do it. I get y prime over y. On the right, it's just the product rule. Derivative of the first is 1 times the second, plus the first times the derivative of the second, which is really just log x plus 1. So now I solve for y prime. Y prime equals y times ln x plus 1. And then finally, I'm going to plug in what y is. It's just x to the x. So y prime equals x to the x times natural log x plus 1. And that's my derivative. So yeah, logarithmic differentiation, pretty much the only way you can do this derivative. Yeah, very, very good. Okay, let's try another one. How about derivative of x to the n? I know what you're thinking. Power rule, right? But let's try it with logarithmic differentiation. So let's let y equal x to the n. That means the natural log of y equals the natural log of x to the n, which of course I can simplify to be n times natural log of x. Note that n is a constant because I'm treating x as the variable, right? I say d by dx. Okay, well now let's differentiate both sides. So on the right, or on the left, I get y prime over y, just like always. What do I get on the left? I get the derivative of n log x. N is a constant, so I just pull it out, and I get n times 1 over x, or n over x. Okay, so y prime equals y times n over x. But y is x to the n, so I get n times x to the n divided by x, which is n x to the n minus 1. And that is equal to y prime, which is the derivative of x to the n. Hey, that looks familiar. I think we proved the power rule. You may recall I told you a few weeks ago, once we know more about the chain rule, we can prove the power rule. There it is. That's the power rule. Proved using logarithmic. Very, very powerful. Logarithmic differentiation. It helps deal with exponent. Okay, let's try one more, a little more complicated one. We want to differentiate sine x to the log x. No, I have no idea what this function would ever model, why you would ever use it, except that it's fun. So the process is always the same. We let y equal sine x to the log x. We take the natural log of both sides. Usually we just pull out the exponent right in front. So that's this natural log. It's going to come right out in front. And then times natural log of sine x. Now we differentiate both sides. So we get y prime over y equals. We have to differentiate this with the product rule. So it's always going to be a product rule, right? Because logs turn exponents into products. But we know the product rule. So we take derivative of log x, that's 1 over x, times the rest of the stuff. Then we add the first times the derivative of log sine x. That's going to be a chain rule, right? Log is the outside, sine is the inside. So we get 1 over sine x times the derivative of sine x, which is negative cosine x. Okay? So y prime is going to be ln of sine x over x. That's a prime, y prime, plus natural log of, and now would you mind if I wrote this as negative cotangent? Of course you wouldn't, you love the cotangent. And then I need to multiply all of this by y, which was sine x to the ln x. Okay, so you don't have to write out all the steps every time, but you should write out enough that you know what you're doing. I would say that I've seen students try to like memorize a formula or skip lots of steps on these. It never goes well. Try to do the steps in order. Okay, so when you use this, pretty much the only time you use it, when you have to use it, is when you have an exponent where there's functions of x in the base and functions of x in the exponent. Okay, so like x to the x, this has x stuff in the base, x stuff in the exponent. That's the main time you use logarithmic differentiation. You can sometimes use it to simplify square roots of fractions and things like that, but you don't have to. For exponents in the base and exponent together, you have to use logs. Okay, so this is a really powerful technique. I really love it. I think you will too. We'll use it in class. I'll see you then.